In the last chapter, we have studied the domain analysis. We know that the both domain analysis and application analysis belonging to the analyze stage. It means that for the analyze stage, it consists of two steps, and in the last steps, it's mainly focus on the static structure of objects and their static relationships, and also there are some state models, but the state model only focus on the state changes of within the object. So besides the static structure, the interactions among objects and between the object and the actors are also very important. So in this chapter, for the application analysis, we will consider the interactions among objects and actors. And also we will add some major application artifacts to the domain model, which are important and visible to users. Because in the domain analysis stage, we didn't consider the application artifacts. We only consider the objects with real-world counterparts. So it means that in the domain models, we only focus on static structure, and after we have completed the domain models, we then shift our attention to the details of an application and consider interactions. So the steps of application analysis is as follows. At first, we should determine the system boundary, and then we should find actors, identify use case, and find some initial and final events, and flash use case out with scenario and sequence diagrams. Prepare activity diagram for use cases that are complex and check against the domain class model to ensure that there are no inconsistencies. So the first is determining the system boundary. The main goal of determining the system boundaries is to determine the precise scope of the application. And the system can be treated as a black box, and the precise scope of application must be known. To specify the functionality, it means that we must determine which should be included and which shouldn't be included in the system. And during analysis, you determine the purpose of system and the view that it presents to its actor. It means during this analyze stage, we don't focus on the implementation. We only focus on their external behaviors. You can change the internal implementation as long as you maintain the external behavior. It means that during the analyze stage, we're only modeling based on the external behavior of objects. This is also the reason why we can fix the flaws very easily during the analyze stage. And usually you shouldn't consider humans as part of a system, which are usually actors that interact with the system. The second is find actors. Once the system boundary is determined, the external objects that interact directly with the system must be identified. It means we should find which objects will interact with the system we considered. So usually, humans, external devices, and other software systems can be actors. You should remember that all of them are not under control of the application we are developing. Actor behaviors are unpredictable because they are not under the control of the system. So applications should be robust to actor behaviors. And we also need to examine each external object to see if it has several distinct faces. It means that different phases should be modeled as different actors. And an actor is a coherent phase presented to the system, and different kinds of external objects can have the same facet. For example, a particular person may be both a bank teller and a customer of the same bank. It means the same person, the same object have different facets. The bank will communicate with the ATM application to process the transactions and so on. And the consortium will communicate with bank and the customer because the ATM application is usually connected with the consortium directly, and then the consortium will clear the transaction with each banks or with different banks. Then the third is find the use case. Okay, the steps is for finding the use case, we need to, for each actor, we should list the ways in which the actors use the system, and each of these ways is a use case. It means we should focus on the use case, focus on the actor, and focus on the interaction of the actor with the system, and each kind of interaction may be a use case. And the use cases partitions the functionality of a system into a small number of discrete units. And all system behavior must fall under some use case. That means that the use case must cover the whole system, and each use case should represent a kind of service that the system provides values to the actor. It means you should divide the system appropriately, and it is better that each use case provides some value to users or to actors, and try to keep all use cases at the same abstraction level. For example, apply for a loan and withdraw cash from saving account using ATM. It is obvious that the later description is more detailed than the former. So, make withdraw would be a better match with the apply for a loan. So, this is a kind of balance in terms of the description. Also, we should in the granularity of function, we should also consider to keep balance between different use cases to make them have the same scale. For example, this is a use case for the ATM example. It has 4 use cases and 3 actors, 4 use cases, and the actor connect with different use cases. And this is the use case diagram we have studied. Okay, after we have finished the use case diagram, we know that the use case don't show the behavior clearly. It only shows a very high level division of the system and some interaction, and only label the actors and the name of the use case. But to understand the behavior, you must understand the execution sequence that cover each use case. It means that we must if we want to understand each use case, we must understand the execution sequence of the use case. So the basis of understand the execution sequence of a use case is to determine the initial and the final event. So the initial event is the actor initiates the use case and defines the event that it sent to the system. So it's called the initial event. And the final event for use case is terminate the use case. The event terminates the use case. For example, the use case of applying for a loan could continue until the application is submitted, until the loan is granted or rejected, until the money from the loan is delivered, or until the loan is finally paid off and closed. So the model must define the scope according to the context of the application. And following are some examples for the ATM use case. For the initial session use case, the initial event is insertion of a cash card. It means this will generate this use case. And the final use case, the final event is system keeps the cash card. And for the query account, the initial event is request for account date from the customer, and the final event is the delivery of account date by the bank. And process transactions, the initial event is initiation of a transaction, and the final event is committing or aborting the transaction. So it means that the first thing for finding or understanding the execution sequence of a use case is to find the initial and find the final events. Then after we have found the initial and final event, it means that we have determined the boundary of this use case. And then we can, for each use case, we can prepare one or more typical dialogues to get a feel for expected system behavior. It means we have studied the scenario. You know that scenario is used to describe the sequence of describes the execution sequence of a sequence of events of one use case. It means one scenario. For each use case, we know that we may need several or multiple scenarios to describe the use case. And first, we should prepare a normal scenario to illustrate the major interaction and information exchange in this use case. And we know that scenario is a kind of text-based statement, a list of text-based statements. And a scenario is a sequence of events among a set of interacting objects. Sometimes the problem statement generated by the system conception stage may describe the full interaction sequence, but most of the time, this sequence of events or interaction sequence is not included in this kind of statement, and most of the time you have to invent the interaction sequence yourself. And prepare scenario for normal case, it means that interaction without any unusual input or error conditions. And maybe sometimes there are multiple normal scenarios for each use case. Okay, this is an example of normal scenarios. For example, for the initial session, this is use case, use case, use case, use case. This is 4 different use case. In the use case diagram for the ATM, for this use case, we use this is a scenario, this is a normal scenario to illustrate the general behavior of this use case. The scenario is a list of interactions. You can consider it to be a sequence of interactions among different objects or among the system and the actors. For example, the ATM asks the user to insert a card. The user inserts the card cash. The ATM accepts the card and result. It is a description, text-based statement or text-based description about the sequence of events or sequence of interactions. And previously, we have written the normal scenarios for the use case, but we know that there are some special cases such as omitted input, or some error cases, invalid values, and fault to response, and so on. In order to make the use case in order to understand these special cases better, we need to write down some exception scenarios or variations. For example, the ATM can't read the card. You can write a scenario for this kind of condition, and you can also write a scenario for the card has impaired. The ATM taps out, waiting for a response, and so on. Because this is very important for an application, because the actors are not a part of the system. Their behavior is not under control of the application, so the application must be robust. If you want to make the application robust, you must build an appropriate model during the analyze state or during some system design or class design stage. So in the analyze stage, we must consider these special cases or error cases and transferring them into models. It means that during the modeling stage, we should consider these special cases or error cases, and then this kind of consideration will be considered during the implementation stage. If you don't mention it in the modeling stage, the developer cannot understand this better. And all of these are text-based scenarios. Then we know that in order to understand these scenarios better, we need to find out all of the external events in these scenarios, and you can also draw a sequence diagram. Use a sequence diagram to make the scenario, because we know that the sequence diagram is a kind of graphical based notations. They are more clear than the scenario. It means that each scenario can be changed into a sequence diagram. So in order to build a sequence diagram for a scenario, we must find out all of the external event. So what is the external event? External event is that kind of event is transferred among different objects. So all input decisions interrupts interactions to or from users or external devices is a kind of external events. And internal computation steps of objects are not events. A transmittal of information to an object is an event, and we should group together under a single name for events that have the same effect on flow of control, even if their parameter values are different. For example, the enter password is a kind of event, but it may have different choice of parameter values. For example, they have different password values. We don't care much about what is the detailed password. They all belong to the same event, enter password. So this is an example for the events for the processing transaction scenario. It means we have found so many events from the processing transaction scenario. Then after we have found these events, we can transform this this scenario into a sequence diagram like this. The user, ATM, consortium, bank, these three are actors, and this is a system we consider, and this is a sequence diagram for the processing transaction scenario. The user, the ATM first display menu to the user. The user select withdraw, and the ATM, and then the user select account, and ATM request amount, and enter amount, and the ATM verify funds with the consortium, and the consortium verify funds with a bank and confirm funds, and the consortium confirm funds, and the ATM will dispense cash. The user will take cash. Okay, this is a sequence diagram which illustrates the sequence of events for implementing the process transaction. So this kind of graphical based notation is more clear than the text based. And we know that this is a normal scenario. And this is a sequence diagram for the normal scenario. And previously we know that we also need to build some scenarios for the special cases or error cases. So similarly, we can also transform the special cases or error cases, the scenario for the error cases or special cases into sequence diagram. It means we also need to build sequence diagram for the special cases or error cases. And it means that after we have built multiple sequence diagram for each use case, we can understand each use case better because we have know the sequence of interactions. And we can also build activity diagram to handle the business logic. For example, for the card verification use case, we have built an activity diagram. The initial is insert card, and if unreadable, keep card. If readable, it will bad card code or bad account, keep card. If communication done, and return card. If card okay, it will check the account. If account good, it will request password, and if correct the password, then finish the card verification. If multiple password failure, it will also keep card. So this is activity diagram. It describes the logic of the business of this use case. So there are many branches, and this kind of, we know that activity diagram mainly focus on complex logics. It means that if the use case is complex, we can use the activity diagram to illustrate it better. Then we need to check against the domain class model to make them consistent.